AI risk doesn't begin at deployment. It can enter through data, models, code, pipelines, and cloud artifacts long before anything reaches production. In this section, we'll focus on proving where components came from, securing how they move, and continuously validating what gets deployed. So far, we've secured architecture, identity, applications, guardrails, RAG, and cloud posture. Now we shift upstream and ask a different question. Can we trust the datasets, models, artifacts, and pipelines feeding our enterprise AI systems? The AI supply chain is broader than code dependencies. An AI system is assembled from software packages, data sources, model weights, training notebooks, containers, pipelines, registries, and deployment infrastructure. Any one of these can introduce risk or change system behavior. The security goal is to make every handoff verifiable: where it came from, whether it was altered, who approved it, and whether it can be reproduced reliably. Supply chain attacks are especially dangerous because they often happen before the model reaches production. An attacker might publish a lookalike package, exploit a vulnerable dependency, poison training data, alter model weights, or tamper with CI/CD jobs. The result can be a trusted-looking artifact that carries hidden behavior forward. The key lesson is simple. Every input to the AI lifecycle, code, data, models, credentials, and pipelines must be verified. Think of AI supply chain security as a control system, not a final scan. Start with provenance. Know who created each dataset, model, package, and artifact. Protect integrity with signatures, hashes, immutable storage, and controlled promotion. Maintain visibility through SBOMs, MLBOMs, dependency maps, and vulnerability intelligence. Then apply governance through trusted sources, approved registries, exceptions, and deployment gates. Together, these controls make secure deployment repeatable, auditable, and enforceable. A useful mental model is chain of custody. At intake, only trusted code, data, models, and dependencies are allowed in. During build and evaluation, the pipeline creates evidence: SBOMs, scans, secret checks, and test results. Before promotion, artifacts are signed and attested, so provenance is clear. Deployment becomes policy-driven. Admit only approved, signed, low-risk artifacts, and continue monitoring them in production. For AI systems, an SBOM cannot stop at the application package list. It needs to follow the full delivery chain: source code and libraries, container images and operating system packages, AI and machine learning frameworks, and the tools that build, test, train, and deploy the model. That includes items like Fast API, base images, CUDA, PyTorch, TensorFlow, LangChain, tokenizer packages, and deployment automation, with evidence for each dependency. An AI bill of materials extends the traditional SBOM into the full AI asset record. It captures where datasets came from, what licenses or consent limits apply, how the model was trained or fine-tuned, and which environment produced it. It also records evaluation results, intended use, risk classification, approvals, and deployment evidence. The goal is traceability. If a model fails, changes, or is audited, teams can reconstruct its history. Provenance is about establishing trust before use. For every dependency, ask, did it come from an approved source, and can we prove it was not replaced? That means checking the publisher, repository, release history, metadata, hashes, and signatures. Use trusted registries and private mirrors wherever possible. This also helps prevent dependency confusion, where a public package impersonates an internal one. The safe pattern is request, verify, scan, then approve or block before anything reaches build or deployment. Secure builds start by making change intentional. Pin exact dependency versions, including transitive ones, and commit lock files, so production cannot silently pull something new. Then make builds reproducible. The same source, dependencies, and environment should create equivalent artifacts every time. After release, keep monitoring CVEs, package advisories, exploit maturity, and framework security updates. Patch decisions should be based on real risk, exploitability, exposure, model criticality, and available compensating controls. Cryptographic signing turns each artifact into something you can verify, not just something you trust by location. The build system signs containers, model weights, tokenizers, datasets, SBOMs, evaluation reports, and deployment bundles. Policy then checks those signatures before promotion and deployment. This creates a chain of custody across the AI lifecycle. If an artifact is modified, replaced, or produced outside the approved process, verification fails and the release stops. Attestations turn a release into evidence. For each AI artifact, capture where the code came from, who built it, which dependencies were used, what scans ran, and which model evaluations passed. The deployment gate checks that evidence automatically. Valid signatures, a complete SBOM, acceptable vulnerabilities, approved provenance, and risk within threshold. If anything is missing or outside policy, promotion stops before staging or production. Datasets should be treated like executable dependencies because they shape model behavior. Imagine a fraud model retrained on transaction data where some labels were quietly flipped. The model could learn to trust risky patterns. Security starts with knowing provenance, consent, license, and allowed use. Then lock access, freeze immutable snapshots, hash and sign manifests, and validate quality before promotion. Finally, monitor for poisoning signals such as label drift, strange distributions, backdoor triggers, and benchmark leakage while enforcing privacy and retention policies. Notebooks and ML pipelines are part of the production supply chain, not just developer tooling. Secrets, package installs, pull requests, runners, and model artifacts all become trust boundaries. The safest pattern is isolation. Short-lived credentials, reviewed changes, signed outputs, and explicit approval before promotion. From there, monitor for unusual downloads, unexpected artifact changes, strange runner activity, or unauthorized releases. This turns experimentation into a controlled path to production. AI supply chain security is about trust from source to runtime. Know which components you use, prove where they came from, monitor vulnerabilities, and require signatures, attestations, and policy gates. Next, we'll apply that same trust mindset to sourcing and validating models before enterprise adoption.